All right, well, Professor Matt England, thank you so much for joining me. Actually, let me fix one thing on the video. Okay, all right, good. You are at University of New South Wales in Sydney, Australia, and I've been following your work for years. You're an expert on ocean circulation. And so you had a high impact paper come out recently that I saw all over the news about ocean circulation. So why don't you tell me what you found?
Yeah, no, great to join you, Andy. So in this study, what we did is we took a climate model set up a little bit different to the standard climate models the IPCC used for projections. We actually put all of the computational power into the ocean resolution. So we had a very high resolution ocean model, and we coupled that to a sea ice system. And we wanted to run a forced experiment into the future, but we wanted to importantly include the effects of Antarctic ice melt. And just for context, we love the IPCC suite of climate models that are analyzed as part of the CMIP project, the Coupled Model Intercomparison project. Unfortunately, there are two limiting factors for those models. One is that they don't get this dense shelf water formation around Antarctica correctly simulated. And the second is that they don't include the dynamic shelf melt and the ice sheet melt behind it as well. And so both those factors we think are really important for understanding the ocean overturning off Antarctica. Getting those water masses there to start with, clearly you've got to have that. But secondly, to include all the forcings, not just warming of the atmosphere, rainfall changes, wind changes, but also this ice shelf and ice sheet melt behind it.
And so why do we care about the circulation of the ocean? Why is that important?
Yeah, no, it's a really good question. I mean, the oceans basically move heat around the planet. They absorb heat in the tropics, they move it poleward, release that heat into the atmosphere. It's fantastic living on a planet that's covered by ocean because they very kindly moderate the extremes from summer to winter. They moderate the extremes from the tropics to the poles. It's part of the global energy balance. Unfortunately, though, if we change them, and that's what we're doing under greenhouse warming, if we change them, we start to meddle with that transport of heat around the planet. We start to change weather patterns. We can change how El Nino and La Nina cycles play out, but also at the polar caps, we can melt ice and raise sea levels. These overturning circulations, I mean, a lot of your listeners would have heard about the Atlantic overturning in the North Atlantic, and they may not be as familiar with the Antarctic overturning, but these two overturning circulations basically set the global energy balance. They set how the oceans interact with the climate system, and all of human civilization has built up during a relatively stable era. Those circulation patterns are quite stable. They bump around a bit from year to year, but they're in these overturning states that are vigorously bringing water to the interior of the ocean, recirculating it, keeping our oceans healthy from an ecosystem's point of view, but also keeping the planet's climate relatively stable. Under greenhouse gas warming, unfortunately, we're really hitting it hard, with extra warmth, with melting ice at the polar regions, and that's all the evidence we have says that this is changing those circulation patterns, and more change is set to come in the decades that follow.
And we know this has happened in the past because the Younger Dryas, which is about 12,000 years ago, is a period when the Atlantic circulation shut down, and that had this really profound impact on the climate of the Northern Hemisphere. In fact, it's The Day After Tomorrow. The movie The Day After Tomorrow is based on ocean circulation changes. So
and that's a great film. I love that film. It's total sci-fi, loads of physics errors, but it was a great way to bring to the fore the science that we're part of, understanding how the climate system works. And Hollywood blockbuster sci-fi, a lot of people tore it to shreds for its scientific errors, but what sci-fi doesn't take a bit of poetic license and make it a drama that's worth watching rather than a slowly playing out climate change. That's one of the things with the oceans that's really important to think about. This absorption of heat and the way they're moderating our climate system, both without climate change and also at the moment with increasing greenhouse gases, it unfortunately lulls people into a sort of false sense of security because things play out a bit slower because of the oceans, but there's huge payback to that down the track. The fact that they're absorbing heat and carbon comes with significant consequences with thermal expansion, melting ice caps, intensifying tropical cyclones, damaging ecosystems like coral reefs. I mean, the list ocean acidification for carbon. I mean, the list is very long, and it's quite confronting when you look at the global ocean temperatures as they're playing out. Great news, they're absorbing all this heat for us, but with big payback down the track.
So in your analysis, you found that the ocean circulation was slowing down. Basically, you got less water sinking off the coast of Antarctica, and sort of the overturning circulation slowing down. So is that a consequence? Did you find that was a consequence of climate change, or was it just kind of random fluctuations of the system?
No, absolutely. If we look at that circulation system without imposing any, if we run models and we look at that circulation system just with the randomness of the atmosphere bumping around with its weather systems and so on, we see variations from year to year. That's for sure, but they're quite small, and we don't see long-term trends in these simulations that we looked at. And also, if we look at evidence from the observed system, it is an anthropogenic signal. It's a signal of climate change to have these circulation patterns slow down. And in particular in Antarctica, it is the melting of the land ice and the ice shelves over Antarctica that trigger this change. It's such a significant forcing agent already. The nice thing about numerical experiments like this is we could actually run a bunch of scenarios, and we actually allowed the sort of atmospheric changes to play out in one simulation, and then we had another simulation with those atmospheric changes imposed, but also the melting of the ice. And so we could separate out exactly what that meltwater was doing. And no surprise, it was the primary agent. And when I say no surprise, it's because fresh water is not dense. So when you have a salty ocean, that extra salt in the volume of fluid makes it dense. If you make it fresher, dilute its salinity, you make it more buoyant. And so like an oil slick, it doesn't sink, it just sits at the surface of the ocean. And that's quite a rapid change to impose. If you melt the ice shelves there and ice sheets and make that water less dense, straight away it gains buoyancy. And so it's less prone to sinking. We can't get these waters into the interior unless they're dense enough. And so by diluting the salinity, you freshen them, you make them buoyant. And so a lot of people, when they asked, were we surprised? No surprise at all about that physics. That's basic, fundamental seawater physics. We can't change that. If we melt the ice, it makes the water buoyant. It doesn't sink. What surprised us, though, was the pace of change. I wouldn't have thought you could get these massive overturning circulations that are pumping, vast quantities of water to the ocean abyss. It's a machinery that we think is quite hard to slow down, like turning the Titanic off its course, really hard to change its course. But so the 40% slowdown just within a couple of decades from now was a fair bit faster than I thought we would have seen. I thought we might have seen a 10 or 15% slowdown.
Yeah, so just to make sure people understand the mechanism you're talking about. So you have some water at the equator, and it's a parcel of water, and then it moves poleward. And as it moves poleward, you're evaporating water off it. So the water gets saltier and saltier, and it gets denser and denser. And then at some point, it gets close to Antarctica. It's so heavy, it sinks. And so
exactly
what your mechanism is that as you melt this ice, you're adding fresh water, and that stops it from it, that makes it more buoyant, so it doesn't sink. And so that's essentially the mechanism. Do I have that about right?
Yeah, no, exactly. The one thing to add to your description, which was very nice, is that you also pick up an extra saltiness by forming the sea ice around Antarctica. So every winter, a lot of sea ice is formed there. That's a very important way to get these. It's probably why the Antarctic wins out versus the Atlantic in terms of it's got the densest seawater is actually formed around the Antarctic margin, because this ice melt coupled with the process you mentioned with the poleward migration of water losing its fresh water component to the atmosphere. So it's a very important driving mechanism. That sea ice formation gives it that extra salinity kick, and that's why we're concerned at the moment. I mean, we're also seeing a sea ice minimum at the moment around Antarctica for this year. For several decades, sea ice was, if anything, growing, and a lot of people thought, well, the Antarctic's fine. The Arctic is where all the action is, but we've seen a big change in the last decade or so with these Antarctic sea ice values coming down, and like I said, the land ice up on the continent melting rapidly.
So, I mean, what's your personal feeling about this research? Are you worried? Were you surprised when you saw it? Is this like, was it, oh crap? I mean, how did you just sort of internally react to seeing what's clearly bad news?
Yeah, no, it's super confronting. It's a fun experience. I'm sure you have this as well, Andy, that when you do science, in a way, I got into this field because I was fascinated by how the oceans work, how they change climate and weather patterns, and the physics of the oceans just is a fascinating topic. So as a scientist, unpacking what's happening, it's a kind of it's a great thing to do. It's a really exciting, intellectually, it's a really exciting field to be part of. And so in a way, when we do this work, we are chasing that scientific discovery because we're of the curiosity we have with how the system works. But 100%, you kind of go, wow, look at this result. It's really amazing. Oh, hang on, it really sucks. It's terrible news. And if I think about the Earth's ecosystems, we didn't talk about this yet, but this abyssal flow drags along the bottom of the ocean and brings nutrient-rich water back to the surface. Like a fish tank, any of your listeners who've got a fish tank at home or go to the aquarium, you don't want that water to be stagnant. You want it to be overturning, being enriched with oxygen as it sinks to the bottom, and bringing those nutrients that sink out from the biologically productive surface. It rains down to the bottom of the ocean. You want that to come back up to the surface. And cutting off that circulation cell actually starves the upper ocean of nutrients as well over time. It's a slower process to play out, but it's certainly of concern. So yeah, we step back from that initial scientific discovery moment to say this is actually really bad. And there's actually more in our paper. I could show you the diagram up online, but if you look at where the warming occurs, why don't I do that quickly? I've got a bunch of slides here. So one of the things that really concerned me about this work, actually, so that ecosystems impact I spoke about plays out over the course of a century or so for really the impacts to mature. In contrast, this feedback to further warming is more or less synchronous, instantaneous with the slowdown of the overturning circulation. And in particular, this sector here in the Amundsen-Bellinghausen seas, let's get my pointer up. This sector here, in our simulations, that's exactly where we get amplified warming. So when you slow down the circulation, this sinking of water off Antarctica, this section here warms the most rapidly. And it's actually what we call the West Antarctic sector. And it's where we know from paleoclimate records that the ice sheet behind the oceans is most vulnerable. And so this is not good news. A lot of the other sectors around Antarctica didn't see a big warming response when we slow down the circulation in the model, but this sector here has the most rapid response, and it's a concern because what you see with that kind of setup is an amplifying feedback. And what I mean by that is you melt some ice, the West Atlantic sector, you change the circulation, that leads to more warming, which means more ice melt. And so you're actually triggering further change from the initial perturbation to the ice. And that's not what we want to see. In the climate system, we know there are self-limiting and amplifying feedbacks. And this seems to be a place where you get an amplifying feedback. And the paleo records, like I said, show that sector is exactly where, during past interglacials and past warm periods, that's the vulnerable bit of Antarctica. It's where we're seeing the most rapid warming already today. And that's a sign that this change that we simulated for the future, we're already halfway through that.
Yeah, the thing that kind of struck me is, we've been working in sort of climate science for 40 years. We have the climate models, but this was a process that really wasn't well understood or included in the models. And so for all of the millions of lines of code and the decades of effort, there's still these surprises out there that don't really, they're not going to change the sign of the answer, but they could certainly make things a lot worse than we think they are. Much worse than kind of the worst case without it. And I find that to be, I found your results to be quite concerning.
Yeah, no, I 100% agree. And I think it's a really good point that to first order, we had the answer back when Suki Manabe and Kirk Bryan and those guys ran those climate models in the 60s, had a land ocean geometry that matched today's configuration of our planet. We know the answer to first order. Those projections have been robust, and we've seen the pattern of global warming play out very much with this fingerprint of more warming over the land and the oceans, Arctic amplification, all those signatures are there. But in this case, we went to the Antarctic margin and to that bit of the climate models ever since the 60s, but right through to today, plenty of studies have shown that there are a lot of biases at this sort of 1 degree standard resolution that we have in the models that are used by the IPCC. And so, it needs a higher resolution. Once you do that, you get these processes on the shelf correctly. And once you add the ice melt, you get this decline.
Yeah, the Antarctic has always been a problem. So I think that, your work really is working towards us figuring out how to model that region better. And it's not good news when you do that.
No, absolutely not. And it's a part of the region where we know we have the risk of big rates of sea level rise if we accelerate the ice melt there. It's one of the biggest uncertainties. Thermal expansion is already bad for sea level rise. We know fairly accurately how that will play out for the next decades and even to about 2100. The ice melt, the ice shelves and the ice sheets behind them, highly uncertain. It can cut to a very high level of sea level rise because there are non-linearities there, ice shelf cliff instability mechanisms, processes where you get warm water into the grounding lines where you can get a runaway effect, and that warmer water actually feeds on itself and drives an accelerated ice melt there. Those sorts of changes are really concerning, and we know that long term, if you go back in Earth's history, when you take the planet to +1, 2, and hopefully not more, but even +2 degrees Celsius, we can go back through a past history and see that even that level of change, which might not sound too bad to people on a winter's day, let's bring on a couple of degrees extra warmth, that's not bad. But for the ice sheets and ice shelves, we know from Earth's history that level of global warming can translate to loss of ice sheets that bring sea levels many meters actually above today's level, which transforms our coastlines. All the cities we've built up around the world's coasts become unviable at about multiple meters of sea level rise.
Right. Well, Matt England, thank you very much. This has been really great, and I appreciate you taking the time to zoom in from the Southern Hemisphere.
Great to join you, Andy.